My name is Andrew Workington, and today I will be introducing the OS that I am writing, which I've been calling UXRT, an internal or placeholder name. There will be a reference distribution that I have yet to name, but more on that later. Currently, it is basically in a skeletal state. I have only gotten so far as the memory allocator stack for the root server, but I have much of the architecture planned out. Here are my goals for UXRT. It will be a general purpose OS with good support for both desktop, server, and high-end embedded use cases. This seems to be somewhat neglected by current research OS development, Gnode being one notable exception. General purpose OS development is more active in the hobby OS world, though. However, many hobby OS projects don't have quite the same goals that I do. It will give owners and admins more control over the system without patching than mainstream OSs do. Mainstream OSs have been on a creeping trend of what I like to call architectural authoritarianism that has started to become especially apparent over the last 10 plus years. Even Linux hasn't been immune to this. Major parts of the Linux stack like systemd and GNOME have done things like moving policy from scripts to compiled programs, removing configuration options for no particularly good reason, and replacing text-based formats with binary ones, again without any good reason. Being free in terms of licensing shouldn't be an excuse for this kind of thing. UXRT will instead expand scriptability and configurability relative to mainstream OSs. It will have extensive support for overriding or extending basically any service in the system without any need for recompiling or fragile shared library hacks, going far beyond any mainstream OS and most alternative ones as well. Also, text-based formats will be preferred wherever they make sense. The security model will be stronger and more fine-grained than on mainstream OSs. Keeping with the previous points, the admin or owner will be excluded from the threat model, with the possible exception of certain types of embedded systems, although that would be exclusively up to the developers of such devices and not the UXRT project itself. Enhanced security will be fully integrated into the system, and not a hacked-on afterthought like on Linux. The risk of most common OS-level vulnerabilities will be reduced compared to mainstream systems. This should mean a reduced dependence on updates to maintain security, although of course the need for updates won't be completely eliminated. Reliability will be better than conventional OSs even on systems without redundancy. Real-time support will be better than mainstream OSs. There will be no need for dual kernel or virtualized setups to run real-time and general-purpose applications on the same system, although only certain APIs will provide real-time guarantees, which isn't uncommon on other real-time OSs. The GUI will be desktop first, going against the trend of mobile-like environments on desktops. Mobile devices will probably be supported at some point, and I will try to follow a responsive design type model, but I won't compromise support for desktop to support mobile. There will be direct support for compatibility with the majority of Linux applications and drivers, integrated reasonably well with the rest of the system, rather than requiring heavyweight types of virtualization or containerization that limit integration. It will try to stay reasonably familiar to users and developers on Unix-like systems. There will be quite a few things that will be changed relative to conventional Unix, but I will try to change things in ways that are reasonably consistent with the Unix way. When there is no reason to change something from conventional Unix, it will be kept the same. Existing third-party code will be used wherever it doesn't significantly compromise the design, in order to reduce the amount of effort required to develop and maintain the system. Basically, my goal is to write a better Linux than Linux, at least for many use cases. It probably won't be for all of them, though. And here are a few non-goals, which again are consistent with trying to make a better Linux than Linux. It won't be strongly focused on trying to do architectural research or introduce a lot of especially new concepts. Most features of UXRT are already found in existing systems in some form. UXRT will just be incrementally improving on them for the most part. It won't be strongly focused on average consumers. The primary focus will be workstation users, embedded developers, and PC enthusiasts. It won't try to be minimalist throughout. The lower layers will be quite minimalist, but upper layers will be full-featured, and overall the system will have most of the same features as mainstream OSs, and some that they don't have. However, the upper layers will generally be quite modular, and it will be very easy to strip the system down if desired. It won't try to be a perfect utopian system. There have been quite a few projects that tried to write their idea of a perfect OS, but ended up either only producing something very limited or not producing any code at all. UXRT will instead just try to be considerably better than mainstream OSs while still being practical. UXRT will be based on a QNX-like architecture with a few ideas from Plan 9. This is an uncommon architecture, despite QNX being successful and the architecture seeming to be optimal in several ways. Thoth was the earliest example back in the late 70s of this type of system. QNX itself, along with a few other Thoth-like systems, were started back in the 80s, but most of these, other than QNX, were abandoned by the early 90s. VSTA is the most recent complete QNX-like system that I am aware of besides QNX itself, but it has been abandoned for quite a while too. Here are the general architectural features of UXRT that I consider most important. These are also fairly typical of OSs of this type. It has a lightweight real-time microkernel with fast IPC. It will have a lightweight IPC transport layer without marshalling. It will be natively Unix-like with no built-in concept of multiple personalities. Vertical modularity is limited. Each instance of most subsystems is a single process containing all layers of that subsystem, and the file system will be the only service lookup mechanism. Here are the main reasons why I consider QNX-like architecture to be optimal. First, a lightweight real-time microkernel with fast IPC. Lightweight microkernels can be competitive on performance with monolithic kernels. This is especially true when direct process switching is supported, since the server gets to start processing the message as soon as the client has sent it, rather than having to wait an indeterminate amount of time for the kernel to decide to schedule the server again. The minimal trusted computing base is kept as small as possible. Real-time support is easier than with a more heavyweight kernel, since the IPC code paths are kept very short and possibly run a nearly constant time in terms of number of instructions depending on the kernel design. Second, a lightweight IPC transport layer. Many types of APIs are simple enough to not need complex marshalling. This is especially true when services are implemented as special file systems, since this allows many types of interfaces to be broken up into collections of simple files. This includes many services that need high throughput to move bulk data, like disk file systems and network stacks. There is no need to add the overhead of marshalling for these. Similarly, marshalling shouldn't be included in the TCB if services with APIs simple enough to not need it. And marshalling can still be implemented in an optional library for services that do need it. This can be made easier by implementing a message boundary preserving special file type. Next, a natively Unix-like system with no concept of multiple personalities. Multiple personality support adds complexity and often also overhead, which aren't really necessary for a practical OS in today's world. Win32 is the only non-Unix OS API that is still broadly relevant, and Wine already implements Win32 on top of Unix, so there is no need for a standalone Win32 personality, nor does making a better OS require a new non-Unix-like environment. A lot can be improved by simply writing a cleaned up and enhanced Unix-like system instead, and Linux binary compatibility integrates better into a Unix-like system than it would if it were implemented as a separate personality. Similarly, it is easier to integrate LKL to get access to Linux's device drivers, storage stack, and network stack in a Unix-like OS. Next, limited or optional vertical modularity. Separation of subsystems into one process per layer or component adds at least 2 context switches per layer handling a request in a typical case where all layers use RPC like IPC. And protection domains often correspond more to entire subsystem instances rather than components or layers. For instance, all the layers of a storage stack often just deal with the same data at different levels. And where necessary, vertical disaggregation can still be supported by plugin architectures within servers and tap type drivers that allow an upper server to call a lower server. For instance, where partition level encryption is in use, there could be separate disk server processes for the encrypted and decrypted layers. Finally, the file system as the only service lookup mechanism. A VFS that dispatches requests to multiple servers is already going to be present, and adding any kind of parallel lookup mechanism would just add unnecessary complexity. Also, if everything is a file, security is mostly reduced to just file security. Similarly, containerization is mostly just reduced to constructing file system namespaces. Given my goals and what I consider to be an optimal architecture, here are the reasons why I'm writing my own OS rather than contributing to various other projects. Gnode has too much vertical modularity for my liking. It also doesn't integrate Unix compatibility to the degree that I would like. In addition, its IPC transport layer is too heavyweight, with tightly integrated dynamic marshalling. Robogalia, similarly to Gnode, won't have fully integrated Unix compatibility. Also, they have only a very general outline of their architecture and seem to be a long ways off from settling on anything definite. In my opinion, they are trying a bit too hard to be perfect. Redox's kernel IPC is somewhat heavyweight compared to that of QNX or L4 type kernels. It doesn't seem to have real-time support either. Its file system model is both more complicated than it needs to be and also a bit too limiting for my liking. Also, it reinvents the wheel a fair bit. Managarm also has limited real-time support. At the moment, its Unix environment, including its file system model, is basically that of conventional Unix, with few extensions, and it has many services that are accessed outside the file system. Minix has relatively heavyweight IPC and a limited service lookup mechanism. It does provide some extensions to the Unix API, but it doesn't go far enough beyond conventional Unix for my liking, similar to Managarm. Fuchsia is yet another system with fairly heavyweight IPC. It also doesn't have full Unix compatibility. Its Unix compatibility is somewhat more integrated than that of Gnode or Robogalia, but it is still limited. Also, it is mostly just controlled by Google rather than being a true community project. Plan 9 is too minimalist for my liking, and its Unix compatibility is also rather limited. VSTA is too old and doesn't support 64-bit. Implementing a decent security model on it would take a lot of work, since its kernel lacks support for capabilities. Making my own distribution of Linux, BSD, or Illumos would require me to compromise my goals significantly, and if I actually tried to modify a conventional Unix to meet my goals, it would probably take so much effort that I might as well just write my own system. QNX would be fairly close to what I want, and what is missing probably wouldn't be especially difficult to add, but unfortunately, it's proprietary. So basically, I think my best option is to write my own system but incorporate third-party code wherever it makes sense. And here are some of the more specific features of UXRT that I consider to be most important. It uses the SEL4 microkernel, although I may switch to a fork at some point due to differing priorities. SEL4 seems to be more focused on protected replacements for deeply embedded unikernel systems than dynamic general-purpose systems. I am using safer languages like Rust and V extensively for new code, although a lot of C will still be present. Third-party code will be used wherever it makes sense. This will account for most of the C code. Everything truly is a file. Even things like process memory and state will be accessed through special files, in addition to all IPC being file-based. There will be alternative file I/O APIs providing direct access to message registers and a shared buffer to limit the amount of copying that occurs. These will interoperate with the traditional file APIs. The transport layer will automatically copy between the different formats when the client and server use different APIs. The basic security model will be based on per-process permission lists and capability transfers. Role-based access control will be implemented on top of this. Privilege escalation will be managed through a server that associates manifests with binaries. Set user ID and set group ID binaries, as well as the requirement to be root for calling privileged APIs, will both be absent, since the native security model will provide more fine-grained replacements. The process state model will be disaggregated. Most state that is associated directly with processes in other Unix-like OSs will instead be associated with context objects. Some of these correspond to underlying SEL4 context objects like the capability space, virtual address space, and scheduling context. Threads within a process may have different context objects from one another. This also includes process creation. Processes will be completely empty when created, with the parent process setting up the threads in context. Fork and spawn will be wrapper functions. LKL, the Linux kernel library, will be used for things like device drivers, disk file systems, and the network stack, in order to get broad support for those things comparable to that of Linux. There will be a Linux binary compatibility environment based on a library, loader, and several special file systems. The init system will be modular and somewhat similar in architecture to SMF under Solaris, with delegated restarters, but without the databases in XML. It will use C groups sort of similar to those in Linux. There will be an event superserver daemon to replace the many ad hoc event daemons found in most other modern OSs, such as Network Manager, UDEV, and UDisks under Linux, with command invoking units. Login and session management will be integrated with the init system and C groups. The package manager will be based on dpackage and apt with extensions for containerization and functional package management. A new terminal API with pushable filters for things like command editing and completion will be supported. This will be implemented in the pseudo terminal server, which will also be able to use a real serial device as a backend. The standard Windows server will be a policy-free compositor with support for an external X11 style reparenting window manager. Compatibility shims for Wayland clients will be provided. The standard desktop environment will be lightweight and somewhat Mac or Next-like by default, but it will be highly configurable to look and feel like just about anything. Multiple distributions will be supported. This will be more analogous to Illumos, where the entire base system is developed together, than to Linux. I'm going to be providing a reference distribution. This will have its own identity, which will be more prominent. I still have to decide on a name for it, though. UXRT will be more an internal name and a generic name for distributions that aren't direct derivatives of the reference distribution. There will be a tool chain for easily building custom distributions, both embedded in desktop or server. Here's a diagram showing how the system fits together. Everything in blue is a process and everything in green is a library or component within a process. I didn't show all of the servers, just the ones I consider most important. As you can see, the architecture is quite horizontally oriented, similar to QNX, but unlike a lot of other microkernel OSs. The only special process is the root or process server, which can be said to be a part of the core supervisor, along with the kernel, since it is the only process that calls kernel allocation APIs. However, it is a separate program and isn't linked with the kernel like in QNX. There is no distinction between servers and clients at the process level. A server is just a process that exports a file system to other processes. The IPC transport layer is a library that implements read, write, and a few other Unix file system API functions as wrappers directly on top of the kernel IPC system calls. It does have some special semantics in terms of how it is loaded in order to keep a stable API, but is otherwise a normal library. The combination of the IPC transport layer and the kernel IPC calls forms a kind of software bus linking all the processes together. Notably, most Unix file system calls other than read and write, such as open and close, are not part of the transport layer at all, but are instead RPC calls to the VFS manager component within the process server, which are themselves sent over the IPC transport layer using a permanently open file descriptor. All the other user-visible components of the process server are implemented as special file system drivers rather than using the RPC channel. This file system architecture is another difference from QNX, where much of the file system API is implemented at the transport layer level, which has the effect of requiring every server to check permissions, whereas in UXRT, all permission checking is implemented in the process server. Association of permissions with binaries, roles, and users in UXRT is however not handled in the process server, but instead in a separate permission store server. Other process server components include memfs, which handles all user memory allocation, procfs, which provides access to process state, much like in other Unix-like OSs, portfs, which allows servers to export file systems, much like its Plan 9 equivalent, and sysfs, which exposes some miscellaneous process server state. Most other servers have their own extensions to sysfs, which are implemented with union mounts over it. Yet another difference from QNX is that there are no remote file system hooks in the process server. All remote file system clients are just regular servers acting as proxies. As you can see, the device servers are all wrappers around LKL, meaning that they are using Linux drivers. LKL will be built as a shared library with a wrapper around it to provide common UXRT-specific glue code and allow multiple versions to coexist more easily. The LKL-based servers will support loading modules using patched versions of the usual Linux module commands. The one device server that has a major non-glue component that is not part of LKL is a sound server, which co-locates a mixer since the Linux kernel doesn't include one. Here's some pseudocode for the base transport layer read method. I still have yet to implement any actual transport layer code though. This is based on Rust and my mid-level binding crate that implements Rust wrappers for SEL4 objects. The transport layer API will distinguish between the server and client side of a file descriptor, and the semantics will differ somewhat, although a process may have both client and server-side file descriptors open, since like I said before, the process model won't distinguish between clients and servers. Separate endpoints will be used for the read and write sides of a connection in order to simplify the implementation. The read endpoint of the client will function as the write endpoint of the server and vice versa, and similarly a read on the client side will be matched with a write on the server and vice versa. On the client side, both reads and writes will wrap SEL4 call. On the server side, read will call SEL4 receive on the read endpoint to receive the message and SEL4 send to acknowledge receipt. 3 different message formats will be supported. Short messages sent in registers, long messages sent in a shared buffer, and errors, with the message format sent as a label. Here's the write method. Similarly to the read method, it is a wrapper for SEL4 call on the client side. On the server side, it calls SEL4 receive to wait for a read message from the client and SEL4 send to send a reply using a reply capability. These methods are purely internal, with user code calling various wrappers around them. Actually moving the data to be sent in or out of registers and buffers must be done by the caller. Dealing with the specifics of register and buffer messages and converting between them will be left up to the actual user-visible methods, which aren't shown here. Also not shown is any code for dealing with offsets in files of definite size, or returning error statuses to clients. This only deals with pipe-like files where all messages succeed. There are also going to be a few other server-specific methods for dealing with different patterns of reading and writing. And here's what I've got so far. As I said at the beginning, it's very preliminary. I've got a utility to build boot images, a simple in-memory bootloader, a kernel patch to pass the multi-boot info through to the root server, low and mid-level Rust kernel bindings, a mostly complete allocator stack, the beginnings of a library for managing threads, and a root server that performs some basic tests on the multi-boot info and allocators. The allocator stack is based on libraries from Redox and Robogalia and heavily extended, with a dynamic 2-level CSpace allocator, a buddy untyped allocator, and a slab untyped allocator on top of it, and support for dynamic allocation of new slabs in the heap allocator being added. The allocator stack is nearly complete enough that user process support could be built on it. The only major feature required for user processes that is still missing is deallocation of entire vSpaces. Here you can see the system that I've got so far booting in QEMU. Like I said, there's not really much to look at. I haven't really bothered to implement anything that you can interact with, and probably won't until I can actually get a real shell running. Only the bootloader sends any output to the screen. The kernel and root server only output to a serial console at the moment. When I scroll back, you can see the kernel boot messages and the various tests the skeleton root server runs. Here's what I am planning to work on next. Other people are welcome to contribute, although right at the moment there isn't a lot of room to parallelize development because dependencies impose a fairly rigid order in which components must be implemented. However, once the VFS is working, development of the internal drivers could maybe be parallelized, and vSpace deallocation could be completed at any time. Once user processes are working, there will be much more room for parallel development. And here are a few links, including my somewhat disorganized file of notes on the architecture. You can also find these in the video description. I think that's about everything. If you have any questions or suggestions, feel free to leave a comment.